Hi everybody, it's Mr. Mullicash again, back with another fun-filled Calculus 1 video. To be honest, we're almost done with these Calculus 1 videos. There's only going to be one more after this week. Sniff, sniff. But maybe someday soon I'll make some Calculus 2 videos or even Calculus 3 videos if I get to teach the class. But anyway, here's some topics that we're going to talk about this week. The first one is I want to talk a little bit more about the fundamental theorem of calculus, especially when it comes to the derivative of an integral. And the first fundamental theorem of calculus, if you recall, states that the definite integral from a to b of any function that is continuous on the interval is found by taking the antiderivative evaluated at b and subtracting the antiderivative evaluated at a. And this is what we've been using to evaluate definite integrals for a while now, right? Okay. Well, there's a consequence of this that is called the second fundamental theorem of calculus, and some books get these backwards. Some call the first the second and the second the first. I've never really known why, but if you take the derivative of an integral, it's a little bit tricky how it has to be written. So first off, whatever we're taking the derivative of needs to be a function of x, right? And in order for the integral to be a function of x, one of these bad boys has to have an x in it. It has to be an antiderivative evaluated at x, right? So for that to happen, we usually let the upper limit of the integral be x and the lower limit be anything we want that's a number. Okay. Now, because that's an x, we need to make sure that the integrand, the thing that we're integrating, has a different variable temporarily. So we talked about u substitution. This is going to be t. We could use u or some other thing. But essentially what's happening is you're going to find the antiderivative, which is capital F of t, and then you're going to plug in x, and then you're going to plug in a. So let me just kind of talk about this piece right here. This would be capital F of x minus capital F of a. And the reason why that had to be a t is because I had to plug x into something that was not x. These variables are definitely well, not necessarily the same thing. Okay. All right. So what happens if we were to take the derivative of that, right? Well, we know that the derivative of any constant is 0, and the derivative of the antiderivative is, well, it's just the function that we started with, but now it has x in it. Okay. So this is a version of the fundamental theorem of calculus. The reason I'm talking about this though is if you're taking Calculus 1, whether you're one of my students or you're out there at some college or community college, you might encounter a problem where this limit is not x. Okay, so let's say if we wanted to differentiate a function and the limits of the integral were a and x squared. Okay. Well, what we would do is we would evaluate our function at x squared, but we'd have to honor the chain rule. And for me to explain that, and this is a lowercase f in case I didn't make my handwriting clear, to explain that, this piece is capital F of x squared minus capital F of a, right? And then you're going to want to differentiate that with respect to x. And we know that when we differentiate something that's composed of x squared, we have to honor the chain rule, right? So what's the derivative of the antiderivative? It's f, but it's f evaluated at x squared, and then the chain rule applies, right? And then minus 0, because the derivative of any constant is 0. Right? So that's the reason for me talking about this, is that you definitely need to pay attention to this upper limit. Let's see if I can make this big enough to highlight. So if this is not x, then you need to honor the chain rule. In fact, really what was happening is, to be honest, we use the chain rule all the time, right? Technically there's a times 1 out there because 1 is the derivative of x, right? So if it's not x, just remember the chain rule. It's kind of like remember the Alamo, remember the chain rule, okay? So just keep that fact in mind. I thought it was worth mentioning because a lot of people forget to use the chain rule when finding the derivative. It's sort of a very common mistake amongst Calc 1 students is that they forget to use the chain rule, and this is another place where a lot of people forget. So make sure that if this is not x, that you're using the chain rule. Okay, enough said about that. So the next thing we're going to do is to find the area between curves. Okay, and let's say that there are two curves, and we want to look at the graphs of these two curves on the same interval. So we'll just pick an arbitrary interval from A to B, and we'll have one curve is strictly greater than the other curve. So this will be an f of x curve, and then down here there'll be some other curve, g of x. And the goal that we have in mind is from this horizontal line from x equals a to this horizontal line x equals b, we want to figure out how much area there is. Okay, now one way we could do this is we could find the area between f of x and the x-axis, right? So the area just to be clear, the area between f of x and the x-axis on the interval from a to b, we remember that from the fundamental theorem of calculus, right? That area is the integral from a to b of f of x dx, right? Okay, but what that would be is this would be the area from this curve all the way down to the bottom where the x-axis is, right? So what you'd want to do to get the area between f of x and g of x is take this area underneath g of x off. You would subtract that piece off of what I just covered in pink. Okay, so let's talk about that. Okay, so the area, I'm trying to get my pen to work here, the area between g of x and the x-axis on that same interval is the integral from a to b of g of x dx, right? Okay, so the area between curves is the difference between those. Area between f of x and g of x, and my pen is looking pretty horrible right now. So if you're a Mac user, I'm using Epic Pen so that I can write on everything, but it doesn't work all that great for Mac right now. It's definitely a better tool on Windows. I don't have a Windows computer, so hope this is going to work out for the rest of the video. But anyway, the area would be the difference between those, right? We take our first integral and subtract our second integral. Now, because both of these integrals have exactly the same limits, we can write that as one big integral from a to b of the difference between f of x and g of x with respect to x. Okay, so this is the way that you would find the area between two curves. Okay, now if you're learning this for the first time, write that down. You're going to need to use that formula, if you will, quite often. Okay, so instead of doing two problems and then subtracting the answers, just do it all at once and subtract the two functions and just do one integral. It's much easier. Okay. All right, so let's take a look at an example here. And what I'm going to try to do is close this EpicPen thing out and see if I can restart it. Just to get things going a little bit better. Okay. Hopefully everything is working out real well. We'll see. So for example, let's say that we want to do this problem. We want to find the area. Yeah, this is much better. Area between y equals x squared over 2 and y equals 2x minus x squared over 2. Okay, how do we do that? Well, we don't have an interval, right? So the first thing we need to do is find the values of x for which the curves intersect. And these curves are going to intersect because this first graph is an upward parabola and the second one is a downward parabola, right? So they're going to intersect, and we're going to try to find the area between the two parabolas, one pointing up, one pointing down. Okay. So the way that we're going to do that is by solving the equation where we set these two expressions equal to each other. Okay. And because this is quadratic, we're going to set this equal to 0. So I'm going to move both of these terms over to the other side. So I already have my x squared over 2. I want this to equal 0. So both of these terms are going to come over here, and I'm going to write them in pink. So now this is going to be a plus x squared over 2, and this positive 2x is going to be minus 2x. So when I move them over, I subtracted or added the opposite to both sides. Okay, so if you're in Calculus 1, that should make sense already. So half of an x squared plus half of an x squared is an x squared. And we're going to find the solutions by factoring. And this one's pretty easy. We set x equal to 0 or x minus 2 equal to 0. So these are going to be the limits of the integral. In other words, you can see that at 0 and at 2, this is where the two curves intersect each other. Okay? All right. So to find the area between them, we're going to integrate from 0 to 2 of an upper function minus a lower function. Now we got to figure out which one of these functions is on top, and just by a little bit of intuition, I know that the downward parabola has to be on top and the upward facing parabola, or the concave up one, is on the bottom. So this particular function is going to go first. This is the upper function. This is the one on top down here. Okay, so from that I'm going to subtract my lower function. The lower function only has one term, so I can get away with not using parentheses. However, in the future, if this lower function has more than one term, you have to distribute a negative sign. Okay, all right, so we're going to keep on working this out. The rest of this should not be hard. Minus 1/2 and minus 1/2 is 1. We can find the antiderivatives. So this one's going to be x squared, right? 2x squared over 2, the 2's cancel, and this one's going to be x cubed over 3. We're going to evaluate this between x equals 0 and x equals 2 using the fundamental theorem. So we put the 2 in first, right? That's our f of b, and then our f of a is when we put 0 in. So 0 minus 0 is 0. So the answer is 4 minus 8/3. Let's see, that's going to be 12/3 minus 8/3, which is 4/3. So that's exactly how much area there is between this upper parabola and this lower parabola. This shaded area here is exactly 4/3 square units. All right, so that's just a very quick example to get you started on the idea and the concepts of how to find the area between curves. It is very important that you explore which curve is on top and which curve is on bottom, which is greater and which is lesser. And these limits of integration, they came from where the curves intersected. Okay, so sometimes those will be given to you, sometimes they won't be, and you'll have to find them yourself. All right, so the last thing we're going to talk about in this video is instead of area, we're going to do volume. Wow, volume. We're taking it to a whole nother level, right? And these are called volumes of revolution, and I'm going to explain to you what those are. First, I want to, I guess, kind of give you an idea, right? So there's going to be a curve, right? And the curve maybe is the square root of x. So let's just draw the square root of x from 0 to 4. So here's our y-axis, here's our x-axis. And the square root of x kind of looks like this. So this is y equals the square root of x. And when x equals 4, of course, the square root of 4 is 2. So this is the point 4, 2, and it starts at the origin. Okay, so let's say that we have a region that is bounded above by the square root of x and below by the x-axis. Okay, but what we want to do with this region is we want to rotate this around the x-axis. Now, in my house when I was a little kid, we used to have these Christmas ornaments where it would flatten out, and then you could kind of rotate it when you unfolded it, and it would make like a bell or a Christmas ornament. Maybe you've got one of those in your house. So if I draw sort of an aerial view of this x and y axis, so pretend that this is a bird's eye view, right? Instead of you looking straight at the wall, you're kind of like up looking down at your desk. Okay, imagine that. So here's that region, and we're going to rotate that around the x-axis. So when that happens, the reason why I have all these fancy pictures here in the book is because it's hard to draw these yourself. But when that happens, what's going on is there's going to be this kind of thing that happens. It's going to look like a piece of ham at Christmas time, right? It's going to be this big circle at the end, and there's going to be these small circles at the beginning, right? Okay, now these circles have a little bit of thickness, so they're called disks. So let's just take one of these circles right here. Let's just take one of these circles right here. Let's say right here, this length would be the radius of that disk. The radius of that disk. Okay, so we'll call that R. And instead of doing Riemann sums, instead of tabulating rectangles, what we're going to do is we're going to tabulate these solid circular disks. Okay, so let's find out how to find the volume of a disk. Now we knew how to find the area of a rectangle, right? That was dx times the f of x. So f of x is the height of the rectangle, the dx or the delta x is the width, right? So now what's going to happen is we have a thickness of our disk, okay, that is dx. Actually, I should call that delta x until we actually put that in an integral. So for right now, we'll call it delta x. And then that thickness has to be multiplied by the cross-sectional area of a disk, which is pi r squared, right? So pi r squared. Okay. Now, the radius is the exact length of the radius is going to be the difference between the function and the x-axis, right? So what we want to do to get the volume of the solid is we want to go from A to B. In our case, it'll go from 0 to 4. I'll do that problem in a minute. pi, which is a constant, so I can put that outside of the integral. The radius is going to be the length from the function's y value to the x-axis. So that's f of x. We want to square the function's length, right? Because it's r squared. And then when we do the integral, our delta x turns into this thing we call dx. Okay, so this is the formula to find the volume of a solid using disks. Okay, all right, so how do we put that into practice for this, right? So this volume would be the integral from 0 to 4, because that's the region that we picked, pi function squared, pi r squared, times the thickness of each disk. And this one, the reason why I chose the square root of x is because when you square it, it becomes a nice easy function to work with, which is x, right? So the 2 exponent is gone because I squared the square root. And then we're going to do our antiderivative and evaluate that from above x equals 4 and below x equals 0. So that's pi times 4 squared over 2 minus 0 squared over 2. And I know I'm going through these steps pretty quickly, but you can slow down. You can rewind this video and slow it down half the speed or 3/4 speed. You know, you might want to go back and pause the video and see if you can work ahead and do some of these, you know, little nitpicky things from the fundamental theorem of calculus. But in any event, the answer to this, let's see, is going to be 8 pi. So this is 8 pi cubic units is how much volume this space takes up when we take this region and revolve it around the x-axis. So there you go. Okay, we'll do one more example of this and then we'll call it a week. So let's do another one where we have to do this football looking thing. So we'll find the volume of the solid formed by rotating the region between y equals the square root of the sine of x and the x-axis on the interval from 0 to pi. Okay, that's our problem. Now, why pi? Well, because the square root of the sine of x hits the x-axis at exactly the same place where the sine of x hits it, at pi. Okay, so here's our region over here, and when we rotate that around, it looks like a football. It's November as I'm making this video. NFL is in full force. College football is nearing the playoffs. So it's time to maybe think about football a little bit. So how do I do this? Well, I'm going to go from 0 to pi. My formula, if you remember earlier, is pi times our function squared times the thickness of each disk, which is a very minimally small dx. All right, so when we square our function, the square root goes away. If there's no square root, then you have to square it out. You might have to do the FOIL method. You might have to multiply a polynomial times a polynomial. You might have to get creative and do integration by parts, right? So some of these problems can get tricky. This is an introductory video that's just teaching you the concepts, right? Okay. So let me be clear about that. The antiderivative of sine of x is the opposite of the cosine of x. Now let me think about that for a minute, right? If y is opposite of cosine of x, then the derivative is opposite of sine of x, which is sine x. Okay, so the antiderivative of this thing should be this, right? Okay. So what am I going to do with that antiderivative? I'm going to evaluate that between 0 and pi. Let me get rid of all this stuff over here. And I'm going to multiply that answer by pi, right? So I have to do negative cosine pi minus the opposite of the cosine of 0. Cosine pi is negative 1. So that's negative negative 1 minus negative, what's the cosine of 0? 1. Wow, holy negative signs, Batman. That's okay. Keep change, change. Keep change, change. So I do believe 1 plus 1 is 2. So the answer to this is 2 pi. Isn't that neat? So the volume of this football is 2 pi cubic units. Let's see if I can scroll down, and there it is. Yep, it's 2 pi. Now you can also revolve your disks around the y-axis. So if you encounter that, you have to change variables and solve your function for x, and then your interval goes from lower y value to upper y value, and then you have dy for the thickness of each disk. So there's many more examples of this, and then next video, and the last one that I'll make for my playlist, has to do with washers. And so that is if we rotate a region that has space in it after rotating it. So we'll be putting washers together rather than disks. Okay, but that is for next week. So until then, reach out to me if you need help. Like, subscribe, comment. If you want a copy of my book, just ask for it. I'm here to help you guys. So good luck with the rest of Calculus 1. Hang in there. We're almost to the end. See you next week.